Achieving an optimal well performance design is a key factor in maximizing well productivity. The PipSim steady-state multi-phase flow simulator enables engineers to design optimal perforations and evaluate their impact on well productivity. In this video, we build a well model, design a perforation, install the completion, and evaluate the impact of perforations on well productivity parameters, namely the mechanical and dynamic skin components. The PipSim simulator provides a new and unique well-centric workspace for building the well model. The interactive well schematic appears on the left, enabling you to drag and drop well components such as tubing or chokes. We will drag a casing and drop it around the wellhead and select the detailed tubular mode. Let's modify its depth to 8,500 feet and change the default casing by browsing the catalogue to select a 7-inch L80 35 pound per foot casing. We will change the borehole diameter to 8.5 inches and accept the default cement information. We will add a tubing by adding a new row in the tubing section. We change the tubing depth to 8,200 feet and directly enter the information for a 2 7/8 inch tubing, an inside diameter of 2.441 inches, wall thickness of 0.217 inches, and default roughness of 0.001 inches. We will also change the annular fluid for the tubing to brine. On the Deviation Survey tab, we will leave the default vertical option to model a vertical well. The Completions tab will be filled in when we perform the perforation design and install the completion. With the PipSim simulator, you can design new perforations at a depth with or without an existing completion. This example has no existing completion. We will follow the steps to designing new perforations at a chosen depth. We will launch the perforation design task and enter the completion target depth of 8,400 feet. The brine-filled wellbore and borehole diameter have been populated correctly from the well model. In the tubular section, the pipes that are present at the completion depth of 8,400 feet have been automatically populated. The simulation task will model the creation of perforation tunnels through these pipes and into the formation for the selected perforation guns. The interactive wellbore schematic on the right automatically updates as changes are made to display the current configuration of the wellbore. We now move to the Rock Data tab. For this example, the fluid type will be oil and a reservoir pressure of 2,870 psia will be used. The rock type is sandstone, and we will assume the default values for bulk density, porosity, rock strength, and vertical stress, which is the overburden pressure. Let's assume the damaged zone or zone of reduced permeability around the wellbore due to the drilling and completion fluids extends 6 inches radially from the wellbore. The perforation gun system selected must create perforation tunnels that extend beyond the 6 inches of damage to connect with the undamaged reservoir. Additionally, the tunnels must be as clean and unobstructed as possible. We will now select the perforation gun systems by browsing the extensive Schlumberger perforation gun catalog. It is automatically filtered to only display guns that will fit into the innermost tubular at the completion depth, which in this example is the 7-inch casing. We will now select two guns, the 5-inch high shot density HSD 135 12 system with PowerJet 4512 HMX charges and the 4.72-inch pure 135 12 system with PowerJet Nova 4512 HMX extra deep penetrating shaped charges. Both systems have 135/45 degree phasing with 12 shots per foot. The PowerJet Nova system is Schlumberger's most advanced shaped charge technology, developed with a penetration-optimized design based on extensive laboratory research involving hundreds of shaped charge test shots into a broad range of stressed rocks, including extreme values of rock strength. Additional gun systems could be added for sensitivity analysis to evaluate their performance, but we will limit ourselves to two in this example. We will change the position of both guns to centered. The well schematic on the right is updated to reflect this. When the row for each perforation gun system is selected, the carrier, charge, and API test data are displayed. Some of this information can be modified. The perforation design simulation can now be run. The simulation determines the rock penetration and entrance hole diameters for the perforation tunnels that will be created for the selected gun systems at the wellbore and tubular conditions. It has two penetration models, the standard unstressed concrete model and the more accurate and robust stressed rock model, developed from years of research by Schlumberger-Rasharon Production Services. The rock-based model provides more realistic results. When the simulation is run, the Results tab will be active and you can view a high-level summary of the simulation results. These include the penetration lengths and diameters for the selected gun systems. Refer to the PipESim online help to understand the differences between the calculated results. The most important results to compare among gun systems are the penetration length and diameter in the formation itself. In this example, it is clear that the 4.72-inch pure PowerJet Nova 4512 creates the deepest and largest penetration tunnels, with a length of 18 inches and diameter of 0.87 inches. These tunnels also extend far beyond the 6 inches of formation damage, which implies that this gun system would result in a successful perforation job. Detailed penetration results can be reviewed in the multi-page report on the Report tab. Up to this point, we have run the penetration workflow, which has provided specifically the penetration results of the selected gun systems. While this information is useful, it would be far more valuable to incorporate these penetration results to calculate productivity parameters such as the skin, which are a better indicator of overall well performance. This involves taking the workflow further by running the productivity workflow. Let's install the completion associated with the 4.72-inch pure gun system, which we determined has the better penetration results. We will select it and click the Install Completion button. We will now exit the task and go to the Completions tab of the Well editor. The task has correctly installed the completion and populated some of the properties, such as the reservoir pressure damaged zone thickness, and the perforation parameters such as shot density, diameter, length, and phase angle. The installed completion has also set the Darcy IPR model, which supports the skin calculations required for well productivity. We will enter the following missing reservoir properties: temperature of 241 degrees Fahrenheit, reservoir thickness of 20 feet, and reservoir permeability of 100 millidarcy. We will enter the following missing skin information: damaged zone to unaltered reservoir permeability ratio of 0.8, perforated interval ratio of 0.9, permeability anisotropy ratio of 0.1, crushed zone to unaltered reservoir permeability ratio of 0.9, and crushed zone thickness of 0.25 inches. A fluid must be defined for the skin components to be calculated. We will define a black oil fluid on the Fluid Model subtab with the following properties: a water cut of 0%, gas-oil ratio of 500 standard cubic feet per stock tank barrel, gas-specific gravity of 0.7, and API gravity of 32 degrees. We leave all other fields set to their default values. Returning to the Skin subtab, we observe that the mechanical skin has been calculated as negative 0.653 and the rate-dependent skin as 3.89 e to the minus 5. It is important to note that these calculated skin values are for the completion you installed with the 4.72-inch pure gun system. It is important to calculate the skin values for all the selected gun systems to determine whether the 4.72-inch pure gun system is still the best option from a productivity perspective. This requires rerunning the perforation design task. Because the well model currently has an installed completion with the Darcy model defined with the various skin elements, running the perforation design task will now run the productivity workflow. The task will calculate the skin components for each gun system using the perforation lengths and diameters simulated in the task, as well as the other skin input parameters in the well model. The Results tab is now updated to show the productivity results in addition to the previous perforation results. It is clear that the already installed completion associated with the 4.72-inch pure gun system is still the better option, because it has a lower skin. In this case, there is no need to install another gun system. We can now exit the task and continue the workflow by running a nodal analysis to determine the actual well deliverability considering both the inflow and outflow. Before doing that, let's return to the well model. The inflow performance relationship curve is displayed on the Reservoir subtab. We check the box to use the Vogel equation below bubble point, and the inflow performance relationship curve updates to show the Vogel correction for two-phase effects. Look at the well schematic. We can see a dual flow path represented by green lines with arrows. Based on the current well schematic, the reservoir will produce concurrently through the annulus and the tubing. To isolate the fluid flow to a singular path through the tubing, we add a packet at 8,150 feet. This completes the process of building the well model. Now the nodal analysis simulation task can be run to determine the well deliverability. Using nodal analysis, we can determine how much production can be expected at the surface from a specified inflow and outflow. PipSim accounts for changes in fluid behavior, pressure losses across the flow path, and heat transfer with the surroundings, and enables you to sensitize on various inflow and outflow parameters to optimize the well performance. We will select the Olga S vertical flow correlation and launch the nodal analysis task. We will select the bottom hole as the nodal point and run the task with an outlet pressure of 200 psia at the wellhead. A nodal analysis systems plot is displayed that shows the inflow and outflow curves and the operating point of approximately 1,698 stock tank barrels of oil per day and 1968 psia. This is the flow rate that would be achieved with the completion we designed in the perforation design task, based on specified well and fluid properties. At this stage, the analysis could be further extended by, for example, running sensitivity analysis on various inflow and outflow parameters, including the perforation parameters such as shot density, and evaluating their impact on well performance. With the integration of perforation design in PipSim, engineers are able to design optimal completions and evaluate their impact on skin and well productivity.